Okay, so I was actually thinking about doing one more video on stocks because I wanted to talk about the étal space of a sheaf, which is a way that we can turn a pre-sheaf into a sheaf in a very natural way. And it sort of captures this idea about, we've talked about this local to global phenomenon. So I have these stocks which are these sort of local versions of my sheaf. Can I glue those back together to recover the information of my sheaf? And the answer is essentially yes. But I've just been kind of finicky about the way I wanted to explain that. So I'm maybe going to put that off until there's a good time and place for us to revisit this in a categorical language anyways. So yeah. Okay. So what am I doing in today's video? Well, I've decided we're just going to start jumping over to the category theory stuff now. Now, if you're not familiar with category theory, that's okay, because this is really going to be a sort of introduction through examples. In fact, I'm not going to give the full proper definition of a category in this video, just because I don't want to teach an introduction to category theory. But in the comments down below, I'll put a link to a PDF that I really like by Tom Leinster. You can look at the full proper definition of a category in there. But this is going to be the more intuitive definition, and then we're going to start to see why that language is useful for us in our context of sheaves and pre-sheaves. So in short, so here's the quick definition of a category. A category is really two collections satisfying various properties. So one collection is called the objects. We have another collection, which is itself a collection of morphisms. So right off the bat, let's talk about the example of the category of sets, right? So the objects are something that forms what one would call a proper class. Why is that? Well, for example, you might want to talk about the entire universe of set theory, right? And we know from set theory, there can't be a set that contains all sets. So our objects can't possibly be a set. They must be this larger thing called a proper class. And there's a whole, theory about those and its interaction with set theory. We're going to ignore it, basically, shove it under the rug, and just take it as this place where we can have things happening on the level of entire sets, right? Or we can have whole universes of stuff. It's going to be very useful for us. So we have our objects is just some proper class, okay, whatever that might be. For example, our objects could be all ZFC sets, right? Our morphisms then are basically we have some sort of arrow between every pair of objects X and Y, and we have a class of all arrows between X and Y, and our arrows have to satisfy some basic things. So let's jump back to this example of sets, right? So I'm defining the category of sets. Its objects are sets, and what are the morphisms between them? Well, they're functions, right? They're going to be functions between sets. What are things that what are properties, some properties of functions between sets? Well, you always have an identity function from every set to itself that does nothing. And by does nothing, I mean, if I called this f, it's always the case that if I were to compose f with the identity function, or rather, if I have any other function from A to A, then it must be the case that 1A composed with G is the same thing as G composed with the identity is just G, right? So sort of like the identity axiom of a group. Hint, hint. There's interesting categorical stuff there. So I have this, I have that I can compose functions, right? If I have a function from A to B and from B to C, then I can compose these to get another function from A to C, and composition is associative, right? So that's basically the datum of a category. You can look at the definition yourself and see all the things that we're going to talk about fit into there, right? So example one of a category is the category of sets. And by which I mean we have a proper class of objects. And for every pair of objects, we have a class of morphisms between them, which we can think of, doesn't have to be literal functions because the things we're dealing with don't even have to be sets, but we sort of think of them as if they're functions, and we can compose them and whatnot. So what are some other examples of categories? Well, this is one that you will often see in algebraic geometry, but it's maybe not so common to see it right at the beginning of category theory. Well, let me just name drop a couple others. So if you have the class of all groups and all group homomorphisms between them, that's a category. In year one of university, you study the category of vector spaces, although we don't say those words, but what is it? You're studying the proper class of all vector spaces. Typically you start with just over the field R, and you look at the linear transformations between those, right? So these are all examples of categories. They have identities. You can compose your maps between them, and of course these are somehow all just sub-constructions. In fact, there is a notion of subcategory, and these are subcategories of sets, right? Because groups, vector spaces, these are all things we normally encounter in set theoretic foundations. But here's maybe a weirder example. So fix a topological space X, and the objects of my category are going to be O of X. What is O of X? This is simply the set of all open subsets of X, right? So those are the objects in my category. And what are all my arrows? Well, I'm only going to say that there's an arrow, a morphism from U to V, if and only if U is contained in V. And in fact, I'm going to let this be the natural inclusion map from U into V. So, this means, for example, if U is strictly contained in V, then I don't have any arrow going in the opposite direction, right? And of course, I have an identity, right? I have an identity that does all the things identities do because U is contained in U. And this defines a category, right? We have objects. I've specified what the morphisms are, and really the only thing to check is that you can compose in an associative manner these morphisms. And again, these are just set functions, so yes, we can do it. And I need an identity, and okay, you can check that. So that's maybe a weird thing. Like, why even bother talking about this thing as a category? Well, if eventually the series we get to some real abstract sheaf theory, we'll see the utility in that. But even coming up right away, we're going to see a manifestation of why that matters. Okay, so we've got this, given any topological space X, we can associate this category defined by its open sets. And let me also remind you of what a functor is. So if you have two categories, say C and D, right? So I mean, the whole idea of category theory is time and time again throughout your undergrad, master's, whatever. How do you study a subject, particularly algebraic ones? You talk about objects, and you study maps between them, right? Groups, group homomorphisms, topological spaces, continuous maps. Banach spaces, continuous maps, right? Graphs, graph homomorphisms. So categories themselves, categories form objects, unto themselves. We can think about things in such a way. So what should be a map between categories? What should be an arrow between categories? Well, that's what a functor is. So basically, a functor is going to take, as input, it's going to take an object. And this is a bit of abusive notation, writing that this is in obj, because this doesn't have to be a set, but it's something that takes in objects of the first category, C, and it returns objects of the second category, being D, right? Okay, just like a function would. And well, in all these cases, we care about structure preserving maps, right? So like a morphism of topological spaces should be continuous. It preserves continuous sets, right? Or open sets. Group homomorphisms preserve the group operation, right? So what do we have in categories? I mean, the only really interesting feature that all categories have in common is that they have a composition of morphisms, right? So not only do I need to, for each object, A, supply an object in the target category, but if I have a morphism from A to B, then my functor better provide me with a morphism between the images of those two objects. And of course, this better respect the composition law, right? That is, if I have two maps, F and G, F composed with F and G should be F at F composed with F at G. So you might be thinking, well, the like one concrete example of a category we've looked at so far, well, I guess two. Suppose I have, right? Suppose I have a continuous map F from X to Y. Does that give me a functor between the category of open sets of X and the category of open sets of Y? In the Ford's direction, it's not so clear though, right? Because suppose I have an open set in X, how do I use F to get an open set in Y? If F isn't an open mapping, I don't get one. So something interesting happens here. Things flip around, right? So I know that instead, if I have an open set V of Y, then its inverse image, by definition, is an open set in X, and it will respect containment, right? If I have some U in V, then the preimage of U will be in the preimage of V. So in other words, given a functor, given a continuous map from X to Y, one gets a functor, we can maybe call it F star, by taking inverse images from the category of open sets to Y to the category of open sets to X. Okay. So let me give you now the uber abstract definition of a presheaf. A presheaf, in general, well, hang on a second. Let me, before I go uber abstract, let me say this. A presheaf, in the sense that we already know it, right? In the definition I gave in the beginning of the series, this defines a functor, or let me say, almost defines a functor from the open sets on X to the category of sets. And again, we talked about how, sometimes we actually want, our presheaves to be, take on values of abelian groups or modules or something. But in standard foundations, those can all be realized as subcategories of sets. So the more general thing is to just say sets for now. But why do I say almost defines a functor? What does that mean? Well, remember that it has to respect arrow composition, right? If I have A to B, then my functor has to, give me a map from f of A to f of B. And if I start trying to show you that a presheaf is a functor, right? Because well, why should we even believe this in the first place? I mean, remember that for us a presheaf, right? It ate open sets and it spat out sets, or groups or rings or whatever. So there's at least hope, because on the level of objects, right, a presheaf, since it eats open sets, on the level of objects, it certainly defines a map from the objects of our category of open sets to the category of sets. What about morphisms, though? Well, remember our in this category, our morphisms only exist when U is a subset of V. And remember that our functor, or rather our presheaf axioms, said that if U were a subset of V, then you get a restriction map from the sheaf over V to the presheaf over U, right? But so therein lies the problem. Here, right, the arrow is oriented in the same way. If it goes from f of A to f of B, or sorry, if the arrow goes from A to B, then, the resulting arrow better go from f of A to f of B. But here the order is flipped around, right? Here the order is flipped around. And you can check that the other properties are satisfied, right? So this functor is going to respect composition, right? Or it's almost a functor between these categories. It respects the composition of arrows. We have maps from objects to objects. The problem is it flips the arrow around, right? And if that's the only thing that's missing, then we probably want some sort of language to be able to discuss that missing case. So here is one motivation for introducing the following, and that's the opposite category. So if you have a category C, then C op, this is simply going to be the category whose the objects are the same, has the same objects as C, but now the morphisms are flipped. So I'm not being rigorous and precise when I say this. Like, there is a very formal way to like construct a category with literal classes and morphisms, and you use some sort of like infinite graph theory or something. But really all you just think of saying is that, well, okay, it's going to be a new category. All my objects are the same, but for every arrow from A to B, I'm just going to create a formal arrow pointing in the other direction, right? So in our category of open sets, say, what are the, if U is contained in V, now it's going to be the case, if this is a proper containment, my collection of morphisms from U into V is going to be empty. And of course, if U and V are equal, I'm going to have one morphism, the identity morphism. And now I'm instead going to have morphisms going from V to U. But what are my morphisms from V to U? It's actually an inclusion map going in the opposite direction, right? So it's just a way where we formally think about maps going in the opposite direction than they normally do, even if it doesn't make sense for there to be a map in the other direction, right? And why? Well, here's one explanation. Now we come to the abstract definition of a pre-sheaf. So, the most abstract definition of a pre-sheaf there is that a pre-sheaf is a functor from some category C. So this actually is defined on any category from C into the opposite category of sets. And now we see as a special case, right, a pre-sheaf in the geometric context that we saw, where we defined it with respect to a topology. A pre-sheaf is a functor from the category of open sets of a topological space into the opposite category of sets, right? And why is that? It's simply because it satisfies all of the axioms of a functor except the arrows, the way that arrows point get flipped around. Okay, so this video was maybe abstract for some people. Let me know in the comments below how it was, if you need, clarification or something. I'm going to just end it there. Let me know how things went. We're gonna make more use of this categorical language, so maybe things will become less abstract as we dive into certain examples, although certainly we're going to start taking this and running with it. So in certain ways, it will become more abstract as well. I just wanted to get a video out because it's been about a week. So hopefully production will speed up, and I'll see you soon.